This last video for 5.6, we're going to switch from growth to decay. So what happens when you go from a growth graph to a decay graph? Well, in growth, as x increases, your y value increases without bound. For a decay graph, as your x increases, your y values decrease towards 0. Now, these two graphs, if you remember way back to, 5.3 when you were first introduced to, or 5.2 when you were first introduced to exponential graphs, is that when you have something decay, right, or you had an a value that was between 0 and 1, that you could call it a reflection of the x values over the y-axis. So in other words, for a growth graph, we have a positive k value, right? Oops, sorry, why is that right? Positive k value, right? K is positive. Whereas when you have a decay graph, when you put the k value in, it's going to come in as negative, and that's going to make your graph decay instead of grow, and that's really the only difference. So it's still going to be that p of t is equal to p naught e to the, but this time negative k t. So it's going to be amount at time t is equal to the initial amount times e to the whatever growth rate you have or decay rate you have times the amount of time that you're going to leave the material. The next thing we're going to talk about as well is half-life. Now, half-life is the amount of time it takes for a substance to decay to half of the original amount. And instead of making things confusing and having a new equation for half-life, they use the same one for doubling time. And so instead of trying to put like a half in here instead of a 2, we just keep a 2, and then all we know is that our k comes out positive, so that when we put it into this equation, the positive k goes in, but there's that negative to make it decay. So we're going to use the exact same shortcut to find half-life as we do doubling time, because it's the same a time to double as it is to half. So let's look at an example. I love these ones. So this is carbon dating. So this is something that is actually done. You have a radioactive element, carbon-14, which is in like most materials on Earth, and it has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? In other words, they find these old things, right? And if they're made of organic matter, they could say, okay, how much carbon-14 is remaining in that material? And because they know how long it takes for carbon-14 to decay, right, their half-life, they can then determine how old that object is. So what have they given us? Well, they've given us that the Dead Sea Scroll lost 22.3% of its carbon-14 at the time it was found, and we want to know how old the linen wrapping is. So we're going to use the equation P of t is equal to P naught, and this time, because it's decaying, we're going to use to the negative KT. Well, what are we going to put in for the amount after time t versus our initial amount? Well, we know that it lost 22.3% of its carbon-14. Well, how much did it have? Well, let's say that it started with 100%. So if you start with 100% and you lose 22.3%, then your amount at time t, so this would be your start or your initial amount, your amount at time t would be 100 minus 22.3, so 100 minus 22.3, which is 77.7%. So that's what we're going to put into our equation. Now, up to you. You can put them in as percentages, because you're going to put, like, it's just kind of a ratio of amount at time t to initial amount. Whether you started with 100 and you now have 77.7, or you start with 1 and you now have 0.777, it'll all work out in the end. Now, I'm going to tell you it is actually easier to do it as a decimal. So we're going to put 0.777 equals 1. E to the negative k times t. Now we know we're solving for t, but we need to know what k is. So how are we going to find k? They didn't give us the decay constant or the rate of decay, but they did give us the half-life. So I know that my equation is that k equals ln 2 divided by capital T. ln 2, so capital T being the time to grow or decay, or double grow or double decay or half decay. That came out wrong. To double its amount or half its amount is what goes in for T. So we're going to put in 5,750. So this is going to be the ln of 2 divided by 5,750, which gives us 0.000120547. And again, I'm going to store that as A, or I'm just going to keep all of those decimal places. Entirely up to you. So I'm going to put into this equation that I'm putting in A, because the way I wrote this, I didn't give myself enough room, right? But just know that I'm taking this number, right? This number is getting written in for K. All right, what are we going to do? Well, now we have to solve for a variable in the exponent, right? We're solving an exponential equation. So the first thing I'm going to do is isolate my power. Well, dividing by 1 is really easy. I've got 0.777 equal to e to the negative. Now I'll write it. 0.000120547. I have a really hard time with zeros. I often write down the wrong number of zeros, which is why I love store and recall, because I don't have to like precisely transcribe something that I already wrote, because I always do it wrong. Okay, now I want you to pause the video. Your choice. Do you want to take the log of both sides to apply the power rule, or do you want to just change this to logarithmic form? Entirely up to you, right? I wish you were here so that I could be like, what do you want to do? I'm going to change to logarithmic form, but maybe pause the video right now and you do what you do. Okay, so I'm going to solve for the exponent. So negative, I would, if this is my work, I'd just write A, but I'm going to be careful. So 0.0001207t equals log to the base e of 0.777. And again, the only difference is if I took the log of both sides, I'd have the log base e of 0.777 equal log to the base e of this. I could bring my exponent down, but I'd still end up with this equal to the ln of 0.777. Okay, so then to solve for t, I've got the ln of 0.777 divided by negative a, or writing it all out, decimal 000, I hope I've written it down right, 120547. Now, I'm going to plug this into my calculator. Now for me, I stored that as A, or you could have it as your answer button, right? I'm going to type in the ln of 0.777 divided by, recall A, or that huge long number. Now, careful actually. For my calculator, if I hit recall A, I'm not allowed to retroactively make it negative, so I have to go back in and put the negative in front of the A. Then, if I hit equals, I get 2093.1 years. So this scroll, if it's lost 22.3% of its organic matter, or carbon-14, then we know that it's 2093 years, approximately. All right, last question. Last question is another decay, but this is going to be oil wells. So oil wells are being drilled and drained all over the world. A particular well is being continuously pumped for oil at a rate of 10% per year. That's my K. Continuous means I can use that base E. What amount will be left in the well after 10 years? Well, let's start by writing my equation. P of T equals P naught E to the negative KT. We want to find the amount after 10 years. So for the amount as a function of 10. Now, how much did I start with? Well, up to you. Do you want to start with 100%? Do you want to start with 1? Do you want to start with 50? You can actually kind of start with whatever you want to. I like to start with 100. I just find when you start with 1, you're left with this weird small decimal and it feels wrong. So I'm going to put 100 times e to the negative 0.10. So my decay rate is 10%. So my equation is going to be to the negative 0.1 t, which is 10. And then I'm going to plug this into my calculator. So I'm going to plug in 100 times e to the exponent bracket negative 0.1 times 10 unbracket equals. And I get 36.8%. So 36.8% will be left. Okay, last one. Last one is how long will it take the well to drop to half of its current level? In other words, t equals ln 2 divided by k. So it's going to be ln 2 divided by the k, so the decay rate is 10%, so decimal 10 or decimal 1. And you don't have to put any negative in there because we're doing it as doubling instead of halving, right? So if we had a half in here, you'd want to put negative so that your time comes out as positive, but don't worry about that unless that's stressing you out. So ln 2 divided by 0.1. So ln 2 divided by 0.1 gives us 6.9 years. So it'll take 6.9 years for your well to drop to half of its current level. All right, hope you enjoyed chapter 5. Logarithms and exponential functions are done. The next chapter that we do is trigonometric functions, and we do that for 2 whole chapters will be in the trig world. So enjoy the end of logarithms.